All right. How are ya? It's Mr. Potts here. This is section 6.1, so the first section of chapter 6. And our theme in chapter 6, um, it's all about polygons and quadrilaterals. So a lot of different polygons we're going to talk about, but really we're going to focus in a lot of in quadrilaterals for many of the sections for this chapter, all the four-sided figures. Um, but to start us off, we're just going to do some general stuff about polygons. And our goal for today, if you want to write that down in your goal sheet, is I can find the sum of the measures of the interior and exterior angles of a polygon. So we're going to deal with the interior angles of a polygon, the exterior angles of a polygon, how we can figure out their measures. So some vocabulary to start us off with. Um, First of all, diagonals of a polygon. All right, if you're talking about the diagonals of a polygon, whoops, not supposed to be like that. Diagonals of a polygon are all the lines from one vertex to the opposite vertices of a polygon. So if you look at this picture right here, those are all diagonals. So a diagonal could be from point A, there's 1, 2, 3, 4, 5 diagonals in this polygon. It's a 1, 2, 3, 4, 5, 6, 7, 8 sided polygon. There's 5 different diagonals, and it makes 1, 2, 3, 4, 5, 6 triangles. A convex polygon is different from a concave. So a convex polygon is a polygon where all interior angles are less than 180 degrees. So if you look at the picture here, a convex is just a regular looking polygon where all the angles inside are less than 180 degrees. Whereas if you look at a concave polygon, which I'll have the definition here, it's a polygon with at least one interior angle that's greater than 180. And if you look right here, this is that angle. On the inside of it, it is an obtuse angle. It's actually more than 180 degrees, so it's more than an obtuse angle. But it is going to be greater than 180 degrees if it's concave. So concave, you think of it, there's a cave being made into the shape. All right, and then there's just 3 different types of polygons that we'll be working with, or called different things: equilateral, equiangular, and then a regular polygon. Equilateral polygon is a polygon kind of like an equilateral triangle, but it's a polygon with all sides congruent. Equiangular polygon just has all angles congruent. And a regular polygon has both equilateral and equiangular. So we're going to be talking about a lot of regular polygons, and those regular polygons have um, all the sides are congruent, and all the angles are congruent. All right, and here's a whole bunch of different types of polygons, and I want to see how many of these you can figure out on your own. Hopefully you can figure out triangle. I've been working a lot with triangles, but try to figure out on your own 4 through 12. And if you can't figure those out, I mean, look them up. Have you looked them up? But then also what you would call a polygon with n sides. All right, so we're going to start with a couple theorems. So the first theorem is Theorem 6.1, first one for the chapter. It's called the Polygon-Angle Sum Theorem, and it's pretty straightforward. If you're looking at the sum of the measures of the interior angles of an n-gon, so an n-gon is just a polygon with n number of sides and angles. The sum of the measures of the interior angles would be n, so however many sides there are, minus 2 times 180. So again, I'm just going to go back to this slide right here. When you look at the diagonals, this is why that theorem makes sense, because when you make the diagonals, um, it makes 6 triangles. It's an 8-sided figure, so 8 minus 2 would get you 6 triangles, and each triangle has 180 degrees in it. So that would be 6 triangles times 180. All right, and that's where this theorem comes from. So if we are dealing with a heptagon, what is the sum of the interior angle measures of a heptagon? Well, hopefully you figured out that a heptagon has 7 sides. So if we use that theorem, we can just plug in 7 for n. So it's n minus 2 times 180. If we have n is 7, so we have 7 minus 2 times 180. That would be 5 times 180, which would get us, if you check it out, I believe that would be 900. So there's 900 total degrees inside of a heptagon. So all the measures are added to 100 or 900 degrees. And the question is, what would you do if you need to find just one of those interior angles? If we know they all add up to 900, well, that's the corollary to this theorem. And hopefully, maybe you could have figured that out on your own. You just divide it by the number of sides there are then. So if we look here, the measure of each interior angle of a regular heptagon is this part right here that we just did from that theorem, the total interior angle sum divided by however many sides there are. All right, we'll do some examples with that. I have one more theorem for you, and this is called the Polygon exterior angle sum theorem. So we're going to look at the exterior angles. Now, exterior angles are not the whole, like it's not this whole piece right here. It's if you were to extend one of the sides, like we have shown in this picture, like this side is extended, the exterior angle, one of them is going to always be 180, but it's this part right here that would be the exterior angle. This one would be an exterior angle, this one would be an exterior angle. The sum of the measures of the exterior angles of a polygon, one at each vertex, is going to be 360 degrees. So these 5 are all going to add up to 360 degrees. That'll work for any polygon. The exterior angles are going to add up to 360 degrees. And when you're just looking at those right there. So the measure of angle 1 plus 2 plus 3 plus 4 plus 5 is going to be 360. So each one, if you wanted to figure out, well, this is my next question. How do you find just one measure or one angle? Well, take 360, divide it by n. So 360 divided by 5, I think it's 72. Trust me, we're gonna go with 72 on that one. Hopefully I'm right. But I'm fairly certain that one is 72 degrees for each one. All right. So lots of questions here based off of those 3 theorems. Well, one of them's a corollary. What is the sum of the measures of the interior angle of a convex, so we're dealing with convex, dodecagon? So hopefully you got dodecagon has 12 sides. We want to know the sum of the measures of the interior angle, so that would be n minus 2 times 180. So it would be 12 minus 2 times 180, which would be 10 times 180. And that would equal 1,000. Oh, whoops. Times 10 would just be 1,800, 1,800 degrees inside of a dodecagon. All right. What is the measure of each interior angle of a regular 20-sided polygon or a 20gon? Each interior angle this time. So we're going to do that. We're going to use that theorem, the n minus 2 times 180 divided by n this time. So if we do that, we'll be doing 20 minus 2 times 180 divided by 20, which would then be 18 times 180 divided by 20, which I'm going to use a calculator for. I'm not going to attempt to do that one in my head. So 18 times 180 divided by 20. So that right there, 3,280 or 40 would be the total inside of a 20-sided figure. Divided by 20 sides, so 162. So that'd be 162 degrees for each angle. Because the more sides you get, the more the angles almost look like they're gonna just be connecting. They're just gonna be straight angles. Well, the more it looks like a circle, so it's gonna be rounded like that. But they're getting closer to 180. They will never be over 180 if it is convex, and regular ones are convex. All right, number 3, what is the measure of each exterior angle of a regular nonagon? So that would be 9-sided. So we just do 360 divided by 9, because exterior angles add up to 360. That leaves you with 40 degrees. All right, number 4, a convex pentagon. So regular convex pentagon, I guess it doesn't say regular, but has interior angles that measure to 90, 100, 110, and 120 degrees. But it's a pentagon, so we need one more side. What is the measure of the 5th angle? So maybe we should figure out how many degrees are inside of a pentagon first. So we do our 5 minus 2 times 180. We're not going to divide that by anything yet. So that would be 3 times 180, which would equal 540 degrees. Now, if we have 90, 100, 110, and 120, I add those up, that's going to be 200, 320. So 90 plus 100 plus 110 plus 120. That's going to be 320. 420, sorry. That's 420. So 540 minus 420. That's going to give me a total of 120 degrees for the last one. All right, again, we're using that theorem. Number 5, the measure of an interior angle of a regular polygon is 156 degrees. Find the number of sides. So now we're going backwards. We have that one interior angle is 156 degrees. So we're going to set that equal to this formula. So we have n minus 2 times 180 divided by n. We want to solve for n. So I think I'm going to do a little bit of rearranging here. So I'm going to multiply both sides by, well, I'm going to move this over actually. Group it, make it smaller, so I have more space. Alright, what I'm going to do with that is I'm going to multiply both sides by n. I don't like this division here. So really we're just doing some algebra here. And then I'm also going to distribute. So I'm going to have 180n minus 360 equals 156n. Alright, so it depends on how you want to work it, but if we subtract 156n from both sides and add 320, whoops, and add 360 to both sides. Trust me, that says 360. We end up having 360 on the right, and 180 minus 156 is 24, so 24n equals 360. Divide both sides by 24, and n equals 360 divided by 24. Oops, wrong thing there. 360 divided by 24 equals 15. So 15 sides here. So find the number of sides in each polygon. Well, in this polygon. And it would be 15 sides. Alright. Now I've got two more, a little bit more challenging ones here. We'll see what time we're at. Alright. So the number 6 says the measure of an interior angle of a regular polygon is 4 times the measure of an exterior angle of the same polygon. What is the name of the polygon? So the measure of an interior angle is 4 times the measure of an exterior angle of the same polygon. So if we think about this here, a triangle would have 180 degrees on the inside. And if you divide 360 by 3, it would be 120 on the outside. So it has to be 4 times the amount. So then I just start building Now you can write an equation for this, or you can make a table for this. There's different ways of solving this one. I'm gonna just make a table and see how if that's quick. If it's not quick, then the equation might be a better choice. So this would be three sides, 4, 5, 6. If I don't get it after that, then I might have to find a better way. So then we'd have 360. We're adding 180 every time. But 360 divided by 4 would be 90. Oh, there it is. Four-sided. What's the name of a polygon? Is a quadrilateral. Because 360 is already 4 times of the exterior angle, which would be 90 degrees. There we go. So that was an easy way to do it. All right, number 7. The sum of the angle measures of a polygon with n sides is 2,340. So we're going to use that um, same theorem, that formula. We have n minus 2. We're trying to find what n would be. N minus 2 times 180. It's going to get us a total of 2,340 degrees. So pretty big. Let me just solve. So we distribute here. Have the 180n minus 360 equals 2,340. We add 360 to both sides. You have 180n by itself. Oops, n equals 0.072. Yeah, 2,700 divided by both sides by 180. This should do the trick. 180 n equals 2,700 divided by 180. 15. Oh, this was the same thing we had before. We had 15 sides. Interesting. Back up by number 5. All right, 15 sides it is. So it's a 15agon, or 15gon, or there might be an actual term for it. You can look it up though. What I'd like you to do then on your own is to finish this by finishing the last couple questions, the closing questions on here, and then move on to working on the homework if you're ready for that. Otherwise, if you have any questions, bring them to me next time you see me, and have a good rest of your day.